All right, good afternoon. I would say welcome back, but that's really only applies to me. um, how was it last week? Enjoy Caleb? It's fun. He's a fun guy. A little biased, but I like his research. And he said that he enjoyed it too. I think he for this class and the other class, I feel like he felt that there's a fair bit of interest and engagement. So thank you for that. And I should bring up the syllabus here. So that'll be kind of the type of topic we will cover in a little more depth after the next exam. So let me pull up the syllabus. All right, so just to kind of orient myself, if not all of you, I realized I don't want any of that. Go away. Realized we didn't have much more time this week before the exam. So for some reason, I felt like I would come back and then we'd have like another lecture on adsorption and then kind of move on from there. But we don't have time for that. So exam is Thursday, and that means today homework is due, and we're going to talk about that. So if you have, and that's the plan. I don't feel as prepared as I would like to, but I think we'll get through it. And I also feel like I know that I have content that I could give you more on adsorption, but I think what I did have you cover online was enough to get through the homeworks. So we can go a little deeper, maybe on some surface. If we take a look at the kind of colloidal principles, perhaps you missed out on that part, and I have a lecture I could give you on that. So I might shuffle things around a little bit back here, but for now we'll just take it 1 week at a time and deal with homework 2 and exam 2. Okay. Questions? Yeah. No. And the in-person exam definitely wouldn't be that level, for sure. If I give you a take-home exam, that would mean that I potentially should make it harder than I would in person, right? Since you have more access to everything. Okay, so let me just let me do this. Let me just take a quick look at what the exam file looked like last time. Okay, so for example, last time I gave an exam, I had a question on how much, given some circumstance, removing some organic contaminant with a powdered activated carbon, given some adsorption isotherm parameters, how much carbon would be used per liter of wastewater in an equilibrated process to achieve the goal. Okay, that would be A. And B, then what mass of carbon per day. C, if the flow rate doubles, what happens. And D, and this one maybe I wouldn't give, but this was considering the case that it takes a long time to reach equilibrium, well, no, this is discussion, so that would probably be fine. What operational challenges would the facility face in this situation? Would you redesign it? So that's one example of an exam question I've given in the past. It's hopefully a little more straightforward. Still wanting to take home? Okay, I don't mind. Anybody have any objections to a take-home exam? What? Yeah, what would be the time frame for like access to solutions? Yeah, that's a good question. Could probably make it due like Monday at midnight or something. No complaints? I corrected that though. I'm so accused. Yeah. Okay. All right. Well, I'm convinced. Plus, I was out all last week, so if you guys feel like that's going to help you, I'm on board. All right. So I'll plan accordingly. So I will make sure it's posted by class time on Thursday, and we won't meet, so you have that time to use, prepare, whatever, and I'll give you something that's not as deep as the homework. Of course, work on your own. You may use the book, but yeah, use the book. Don't use anything that you're like trying to make something else give you a solution. I want to see your thought. Okay. It's take home. Can't really give you access to the book, so I don't think it makes sense to prevent you from Googling what the Langmuir isotherm is or whatever. So I'm not going to say don't do that, but you know, I wouldn't ever recommend using any AI or anything like that, right? That, you're just going to be doing yourself a disfavor. So, okay, so we'll do take home, and today we'll just do the best we can to make sense of this challenging homework assignment. It's funny, I did make myself a note from last time to like cut back on a couple things, but like going back through it today, and like I had limited amount of time to kind of go back through the solutions today myself, been catching up on everything, and I realized, oh, this is pretty long. So sorry about that. Okay, so let's get to it then. See what we can do. All right. Well, before we even do that, any other major questions or concerns, like big picture about the homework? Any thoughts? Yeah.
Can we like really go in on number 7-2?
7-2, yes.
Like we can like get there when we get there, but like
yeah.
In Excel, I wanna.
Okay. Yeah, that's one part where I thought I had an Excel sheet prepared, and I might have to, I know I have some Excel at least prepped in my solution slides for 8.1, but I might have to revisit that and make that part of a lecture in the future to say, okay, here's how we would do that, because I don't have it. I might be able to do it live, do what we can, but we'll come back to it if we need to. And I'm not giving you any Excel work to do on the take-home exam, unless it's really simple, like, you know, a linear regression or something. But don't know yet, no plans, and I'm not going to make you do a numeric solution on the exam. Okay. All right, so let's get into 5.1. This is a vapor pressure problem, pure liquid benzene at 25 Celsius. We're given a vapor pressure of 0.13 atmospheres. So part A says, if the volatility of benzene followed Raoult's law under all conditions, what would be the partial pressure of an aqueous solution containing 0.1 milligrams per liter of benzene? So I think we'll come back to it in part C, but Raoult's law typically applies to pure liquids and things that are at a very high concentration, so close to a pure liquid, if not a pure liquid. Whereas Henry's law applies in more dilute cases. So this is going to be some sort of a comparison of that, and we're going to run some numbers. Assuming Raoult's law applies, then in part A, we would begin by setting it up accordingly. So we want to know the partial pressure of benzene. And we're going to get to that from first starting with the aqueous concentration is known, 0.1 milligrams per liter benzene. And we have Raoult's law telling us that the partial pressure of some species will be concentration in the liquid divided by concentration of a pure liquid times PV. This would give us the mole fraction. So we can rearrange and say our concentration for the benzene that we want to solve for in the air. Sorry, I'm just, handwriting is not great there. We can take 0.1 milligrams per liter in the water, divide this by the molecular weight to get us, I'm going to go ahead and put the molecular weight of benzene in milligrams per mole, 78,000 milligrams per mole. This will give us an amount of moles, 1.28 times 10 to the minus 6 moles per liter. So we're just converting to concentration in moles per liter. We can also find the concentration of water in liquid water. So if we wanted to know that, we could take the density of water and all that. You may have done this before. I'm just going to remind you that it's kind of a similar thing we can do to find the concentration of a liquid. It's a little funny to say, but how many moles of water are in 1 liter of water, right? And that comes out to be about 55.5 moles per liter. Kind of just a reminder there. Okay, so back to our pressure that we're after. We want pressure of benzene in the air when we have some specific concentration here. This will be that 1.28 times 10 to the minus 6 moles per liter. Divided by concentration of benzene times the concentration of water. Let's see, that's plus. And then we're going to take this and multiply it by the 0.13 atmospheres. That's our pressure, our vapor pressure, excuse me. So we're going to multiply that by 0.13 atmospheres. This will give us a value of 3 times 10 to the minus 9 atmospheres for that scenario. Okay. Okay on that? All right. So part B, and by the way, if you see something I did wrong, I don't really trust my reading of my handwriting, so feel free to point it out. But anyway, part B says, what is the actual partial pressure of benzene in such a solution based on Henry's constant given in table 5.2. So we were given some constants and explain the difference between the values based on the interaction of benzene molecules with one another versus with benzene and water. So the explanation should be something like benzene is happy to interact with each other. They're not very polar. They're going to be, if they can, associating with one another. They don't really like to associate with water because water is rather polar and they're just not mixing very well. So in that case, benzene would probably rather escape from water and go and volatilize, whereas if we consider it under Raoult's law, the benzene molecules are happy to stick together and be together comparatively. So that means if we used Raoult's law to estimate it, as we'll see with the calculations in a moment, that we should be estimating with Raoult's law less in the gas phase and more in the liquid phase compared to what is the real case with water. Okay, so with that, we can say for part B, to calculate it, we get the Henry's law constant 5.56 in atmospheres per mole liter. Thanks. And from here, we can solve for our partial pressure equal to the Henry's law constant times our concentration. So that'll be our 5.56, and then multiplying that by the 1.28 that we calculated earlier. Once we do that calculation, our partial pressure of benzene should be 7.12 times 10 to the minus 6. Okay, and sure enough, that is a much bigger number. So with the water molecules around, benzene's like, yeah, I'm out of here. Just gonna leave. Whereas if we assume that the entire solvation was benzene, benzene's happier to be with benzene than with water, they're gonna hang around in the liquid phase instead. So that would explain the difference there. Okay, part C, explain how the difference in the partial pressures computed is related to the aqueous phase activity coefficient for benzene if the reference is stated as pure benzene at 25 Celsius. So really, the technical way to describe this would be these coefficients. If our gamma value is 1 for pure benzene, it's like an activity coefficient, then the activity, that's annoying, coefficient in a dilute system, we could understand as greater than 1 because it's actively trying to get away from the water. Okay, does that make sense? Good on that? All right, and just to update something, you missed this earlier, but we decided to make the exam on Thursday to be a take-home exam. So I will email everybody to post that as an exam on Moodle. The plan is for it to be due Monday on midnight. Okay, and all right. Okay, so 5.3 is our next problem. We have a water supply reservoir that impounds water principally from melting snow, and therefore it's at 0 Celsius. It's at an elevation of 1,000 meters. Water flows by gravity through a closed conduit pipe to a second reservoir at an elevation of 300 meters, where it warms to 10 degrees Celsius. Assume that barometric pressure is 1 atmosphere at sea level and decreases by 1% every 270 meters. For every 270 meters increase of elevation. question is how much oxygen will enter or leave each liter of water as it equilibrates in the lower reservoir. The molar standard, 25 Celsius, enthalpy of volatilization for oxygen is 13.3 kilojoules per mole. And we can convert that to atmospheres. So the question really is, we have this water, it's up on a platform kind of situation, up at a high reservoir, and it's cold. So it's going to take up probably a lot of oxygen, but there's a little less oxygen up there, so we have to figure out, is that going to be more or less oxygen than it will have when we lower it, where there's more pressure of oxygen but a higher temperature. So which way are we going? Are we gaining or losing oxygen when we make this difference? So if we were to draw something up to kind of conceptualize it, we could say we have water at 1,000 meters, and then it's being piped down to 300 meters. It's not down 300 meters, it's down to 300 meters, so we dropped 700 meters of elevation. And then we can consider what the amount of oxygen in each case would be. And perhaps the best thing to do would be to start with what's the pressure of oxygen in the atmosphere in each scenario. So the pressure of oxygen at 1,000, we could describe this as normally at 1 atmosphere pressure, 21% of the atmosphere is oxygen. So we want to know, well, how much is up here? So we can take that 21%, or 0.21 as a value, multiply that by the amount of change we've observed from the elevation. And to get that, we can say, we can multiply this by essentially 100%, is if 100% corresponds to exactly what's at sea level, meaning the atmosphere, 100% of 1 atmosphere is there, well then if we end up with 90%, we take 90% times our 0.21 to get our percent of oxygen in that new elevation. So what we'll do is we'll take 100% minus this 1% per 270 meters. Okay, so that'll look like this. We'll take 100% minus 1,000 meters times 1% per 270 meters. So that gives us about a 3% change, roughly, a little more than. So if that's, let's say, 97% of the oxygen is there, we'll take 0.21 times approximately 97%. And that'll bring us back to a value of, turns out to be 20.2 or 0.202 atmospheres. Okay, so we'll keep that one in mind. That's going to be helpful. We also need the pressure of oxygen at the 300 meters above sea level. We'll do the same thing, and that will come out to 0.208 atmospheres. It's not an answer yet, but that's just how much oxygen is in the atmosphere at each of these levels. Okay. And of course that means at 0 meters, the partial pressure of oxygen is 0.21. That's kind of the starting point. Okay, so then in order to go from here, the next thing we have to account for is this temperature change. So what we can do is use our equation to handle temperature changes, taking the natural log of H2 over H1 for the H's being the Henry's law constant for oxygen, and we can equate this to our standard enthalpy values for oxygen according to this formula. Okay, so there's a lot of numbers there, but we have everything we need. All we have to do is essentially convert this, get a value for R in the correct units, and ultimately get ourselves a new constant at the two different temperatures, or compare them to our standard constant at 25 Celsius. So we have H at 25. Do I have that written? I don't know if I have that written, but we could look that up. I think that's around 600 something. So, but what we're going to do is calculate H at 10 and H at 0.
H at 25 is 760 atmospheres per mole.
768, yeah, that sounds per mole per liter. Yeah. Okay, so that tracks. So what we're going to do, first of all, for we can put in the numbers. I'm going to try to keep going kind of quick here, but just to show you, we could take 10 over H25 and say that's going to be equal to essentially this this first portion, delta H divided by R. We have numbers for that. It ends up becoming 1600 Kelvin. I guess I can elaborate that on below. But ultimately what we end up getting is 1600 Kelvin times 1 over 298 Kelvin minus 1 over 283 Kelvin. So that'll give us a ratio between our H25 and our H10, and then we can solve for H10. Just as a little aside here, if we were to write this out, the standard enthalpy of volatilization, that was given at 13.3 kilojoules per mole, but we probably want to convert that to atmosphere, so we're going to include that factor, 9.87 that they provided, liters atmosphere per kilojoule. That'll give us atmospheres per mole, and divide that by R, and we can get R as from a lookup table as 0.0821 liters atmosphere per mole Kelvin. So all of that then times the 1 over T1 minus 1 over T2. So all I really want to highlight here is this stuff, if we do that calculation, should give us that 16,000 Kelvin. Okay, so coming back up here then, that's where this piece is coming from. And we can do the same thing with H at 0. And it would look like this. 1 over 298 minus 1 over 273. All of that should be 0.15. I'm being a little shorthand here. Okay, so then we get H at 10. Well, we can get numbers for each of these and then solve for H at 10. So I'm going to shortcut just a little bit here. H at 10 comes out to be something a little bit lower than at 25. This is 579 atmospheres per mole Kelvin, or mole per liter, excuse me. And H at 0 equals 470. Now, finally, with those, we can get concentrations that we expect in the liquid phase for each, and the difference between those will give us the number of milligrams leaving the water per liter. So if we convert those into milligrams per liter, or moles and then to milligrams, then we'll get some mass departing. So, didn't leave myself much space here, but we'll carve out what we can. And we'll say concentration at 0, that's going to be the partial pressure of oxygen at 0 divided by the concentration, or excuse me, the H. Let's do 10 first, not 0. Okay, and we already solved for the pressure, and now we solved for the H10. So now we can get a value of 3.59 times 10 to the minus 4 moles per liter, which we can convert. That becomes 11.4 milligrams per liter. C at 0 then, do the same process. We should get 4.3 times 10 to the minus 4 moles per liter, which becomes 13.77 milligrams per liter. So with that, we can take 13.77 minus the 11.4, and we'll get, don't know why I didn't write that, but that should be about 2.37, if I did that right in my head, milligrams for every liter remaining, or leaving. So we can say 13.77 minus 11.4 equals I think it's 2.37, right? And so I'll just write it here. I can't see behind my the video feed. That's which is why I put the little thing there. So as soon as I'm drawing into this space, I can't see it at all. So I'm like, am I there? Okay. Maybe if I look over here, that'll help. There we go. All right. Makes sense? Yeah, I think so. Just says how much, right? How much oxygen. You could report that in moles. We often talk about dissolved oxygen in milligrams, so probably a good idea, but no big deal. All right. Next up, we have another challenging one. And another gas phase type of thing, but also mass balance here. So here we have a gently mixed pond, has a approximately rectangular surface and a trapezoidal cross-section with dimensions shown in this figure. The hydraulic residence time is given at 6 hours. And we have dissolved oxygen in the influent. It's approximately steady state at 3 milligrams per liter. During the day, algal growth in the pond causes dissolved oxygen concentration to increase up to 16 milligrams per liter then by sundown. And even though the concentration we're in equilibrium with air. If we were in equilibrium with air, it would only be 9 milligrams per liter. The algae are just producing a ton of oxygen. So we end up with a lot of oxygen in the water, oversaturated under the local conditions. Assume that photosynthetic activity stops abruptly when the sun sets at 6 p.m., but that the respiration continues to consume oxygen at a steady rate of 2 milligrams per liter per hour. Now you'll notice that's a steady rate. Going to simplify things a little bit, meaning that it's the rate doesn't depend on how much oxygen is there. And we see from the units, it should be zero order, right? So part of the process uses a zero order. So we'll come back to that. If the overall gas transfer coefficient is 24 centimeters per hour, compute the dissolved oxygen concentration in the pond at 6 a.m. I'm not going to give you something that's challenging on the exam, even though it's take home. You've tempted me, but no. Okay, so this is quite the problem. We need a mass balance to figure out where the oxygen's going, what's happening to it, and how to solve for that. So we will certainly need, from our toolbox, the mass balance, right? We have accumulation will be equal to what's coming in minus what's going out plus whatever kind of reaction terms we have. So this will be plus gas transfer and probably also a rate of consumption. So we're going to have quite a mass balance to solve, and we need to solve for that concentration. It's not going to be at steady state, so we're going to have to account for that, and we have to let it run for 12 hours because that will take us from 6 p.m. sundown to 6 a.m. sunrise kind of thing. Funny enough, last week I was actually at a pig farm that has a wastewater treatment plant that's probably not too much different than this in terms of dimensions and shape and stuff. And in Nicaragua, the sun does set pretty fast and rise pretty fast at around 5 to 6 range on either end of the day. And so it's actually like kind of maybe a reasonable approximation in some ways. Okay, so anyway, so we want DO at 6 a.m. How do we get there? Well, first we know that's going to be 12 hours for our time. And we can go ahead, let's write a few other pieces that we know. We know that the concentration of oxygen during the day is 16 milligrams per liter. We know, in case we need it, at saturation, it's 9 milligrams per liter. Our tau is 6 hours, noted above. We can calculate a volume according to the geometry. I'm just going to skip ahead a little bit and just copy that straight over. Should be 12.5 cubic meters. We can also get a surface area at 15 square meters. Again, a little bit of geometry, but I think I'm confident you guys can get that. Then we have our reaction rate for oxygen consumption, this guy up here. We were actually given a constant rate. So if we go back and read, even my brain just a minute ago was thinking to myself, okay, we have some rate constant, but actually this is probably not even a rate constant, right? This is probably actually the full rate. We're saying respiration consumes oxygen at a steady rate of. So this is actually the full rate term. So we don't have to do the rate constant and all that. We just can plug that in directly into our mass balance up here. So that's actually quite handy. This was just simply given at 2 milligrams per liter per hour. And if we think about it, that is a mass per time unit, except within some volume. Okay, so with that, I think we're ready to embark on the mass balance. Because what we'll need to do is use our gas transfer tools to get a rate for the gas transfer, and then see how we need to solve from there. And it's not going to be a pretty integral, but we're going to make an integral. Okay. So, for the mass balance, we can just go ahead and set it up in some volume. We're tracking the concentration of oxygen over time. What we have coming in is a flow rate. We have some Q entering. So we will have Q, and our initial concentration was given at 3 milligrams per liter. Probably should write that here too. Q, I'll call it C naught. And we can say, or Cn if you like, minus QC leaving. And for our gas transfer, we're going to take in that volume the overall rate constant, the air gas transfer rate constant, K, L, times the surface area, AL, times the difference in concentration at saturation compared to the current. So this will be Cl star minus Cl, the concentration in the liquid, minus the, let me move this a little bit. Minus that last rate, which we can apply as V times R consumption. Okay. Setup look okay? All right. From here, it's just a matter of solving, right? But let's walk through that, or march through it, or whatever you want to call, slog through it. So we'll divide everything by V. I think that'll be convenient in this particular scenario. That'll give us dc dt equals Q over V, which will be 1 over tau. In fact, we could even combine these two terms and kind of keep things a little bit simple to say C naught minus C over tau. Since both of those are Q over V, it's 1 over tau for both. That just kind of simplifies things a little bit. Plus this term, I'm going to keep that as is for the moment, except get rid of the V. And we can get rid of the V for the last term. So it's minus R consumption. All right. From here, we're essentially ready to separate and try to integrate. What we'll notice is we have Cl in a couple spots, in here and in here. And what we want to do is, to whatever extent possible, isolate them and then do our integration accordingly. So we will, on the left side, be integrating essentially from the Cl initial at time 0 to Cl at 6 a.m. at some time t, 12 hours later. And we're going to integrate dc over essentially that entire term. Fortunately, some of it's constant. So what we can do is we can say the C naught over tau. And what I'll do is I'll go ahead and just separate everything we can separate into C in the liquid. In fact, I'll just go ahead and separate it out. Well, yeah, let's just go ahead and separate it out up front. So anytime we have Cl, we want to group that by itself. And I'm going to go ahead and do so by saying this will be CL, and I'm sorry, let me try to rewrite this. Sorry, we have to have a minus. I'll come back to that. I'm gonna put the separation over here. Okay. So we're taking out the CL from the 1 over tau and the KL AL. Over here, then we're left with C naught over tau plus KL AL times our CL star times our rate of consumption minus that stuff. Okay, so assuming I copied that over correctly, that should be correct algebraically. And then on the other side, we simply have integrating dt from 0 to time 12 hours, or time t. That makes a lot more sense. Thanks. Okay, so from there, we're going to try to integrate, right? Now, one thing we can go ahead and do is put in the numbers that we have for the pieces, and that will actually help us visually simplify and say, okay, not all of these are variables that we are trying to integrate. We just have some constants here. How do we handle that? And so we can rewrite this as dc over the incoming is 3 milligrams per liter, divided by 6 hours, plus we're going to have 0.288 per hour times 9 milligrams per liter. And I wrote a lot smaller last time, so maybe I need to just write smaller. Unfortunately, I can't just like tell my font to go smaller, right? Okay, my apologies. I'm going to try to write small. Minus the 2 milligrams per liter per hour minus 1 over 6 hours plus that 288 per hour times our concentration. Okay, so that's that part of it. This will simplify down to integrating dc over, you can put in a lot of those numbers and simplify. This should become 1.09 milligrams per liter per hour minus 0.455 per hour times our concentration in milligrams per liter. So that'll give us milligrams per liter per hour in both terms. Okay, that integration is a little bit more manageable. And so to pick up there, we can say when we do integrate that, it ends up looking like this. T from the other side is equal to, which time is 12 hours in this particular case, but we can say T equals 1 over this negative 1 over 0.455 times the natural log of essentially C over C naught, but with this entire piece for C and C naught. So that will be 1.09 minus 0.455 times CL at time t divided by 1.09 minus 0.455 times C initial. We solve this for C. And we end up with 2.45 milligrams per liter. Okay. Does the process make sense at least? Kind of see how we're navigating that? All right. To me, it's a little surprising that we can get, in a way that we can get, we can answer that problem with a mass balance. It's a pretty neat thing. All right, any other questions here?
On the previous slide, the AL times AL is equal to 0.288. Where does that number come from?
That number will come from the AL will be our surface area, and KL is the 24 centimeters per hour, but we probably need to put that into meters. So 24. So if we take 0.024 meters per hour and multiply that by the surface area, which we found to be 15, yeah, that looks like it should be a fraction. Yeah, that's true. This should be AL is surface area per volume, right? So AL equals SA over V, right? Yeah. Thanks. Okay. Any other questions or issues? Okay. So 7.2, we'll try to do a deep dive here. We have the adsorption of carbon tetrachloride, CCl4, has been studied in batch adsorption tests with pulverized granular activated carbon. Don't know why they didn't just say powdered activated carbon, but sure. In tests, a small amount of carbon tetrachloride was added to bottles containing water and adsorbent. And the system was allowed to equilibrate under well-mixed conditions for 7 days in sealed bottles that were free of gas headspace. Blanks with no adsorbent were run to verify no CCl4 was lost during this process. And at the end of 7 days, the bottles were centrifuged and the equilibrium aqueous concentrations were measured. So we've got a table that was provided, shows the results obtained for the two representative samples. And you notice we've got one with 50 micrograms of adsorbent and one with 10. So we're doing different masses of adsorbent, and we get a bit of data from them. So part A says use this 2-point isotherm to estimate K, so the Kf and N for the Freundlich isotherm equation, and include units where appropriate to describe that system. So just a quick reminder here, and we'll go ahead and start here. The Freundlich isotherm is essentially saying that our adsorbed concentration, Q, is going to be equal to some constant Kf F times C to the n power. And so the question is asking us what is n and what is this k, given a little bit of data. So what we can do here is essentially look at initial versus final to see we have the data to note the concentrations in solution initially and the concentrations in solution finally. We can use those to determine how much concentration is on the adsorbate, excuse me. How much adsorbate is on the adsorbent. Excuse me, and I mentioned earlier, I meant to say we are changing the mass of carbon tetrachloride, not the mass of the GAC. That's the same. Okay, so with that, we can find two different Qs to then essentially look at how to set up an isotherm and derive that. Okay, so we have concentration in the initial case and final. Initially, for bottle A at 0, we would say this would be 50 micrograms per 0.1 liters because we have 100 milliliters. This will give us 500 micrograms per liter. And then for the second bottle, B, this is going to give us 10 micrograms per 0.1 liter or 100 micrograms per liter. And in the final scenarios, CA final, we could say this, do the same thing and find this is 120 micrograms per liter. And for our second vial, this will be 19 micrograms per liter. Okay, so that's all just coming from our table, from the data provided. And with that, we can calculate our Q in bottle A. And we can do this by saying, well, mass balance on the concentration that was taken away from the water is now the concentration that is on the powder. It's on the adsorbent. So we can say this concentration should be C initial minus C final. That's the difference that we've observed, times the volume divided by the mass of adsorbent in the system. So times V divided by M. This will give us, if we look at the units, concentration times volume gives us a mass. So we'll have a mass per mass unit, which is good because that's usually what we do with Q. What mass of adsorbate per mass of adsorbent is what we're looking for. So we can say, in this particular case, for A, this should be 500 minus 120 divided by, we had 20 milligrams, excuse me. So this will be some number of micrograms per milligram, comes out to be 0.41, excuse me, wrong number, 1.9 milligrams of our CCl4 per microgram, did that backwards, micrograms per milligram. Of adsorbate. Okay, so that's QA, and then QB would be same process, comes out to be 0.41 micrograms per milligram. That gives us 2 points, and now we can plot them and make some sort of sense. Probably the best way to do this, we're only given 2 data points, and we want some linear relationship between them, so that we need a straight line between 2 points, but we have the exponent, right? So we have to set this up in a way where we can find n without, with a straight line type of system. So we'll take the natural log of both sides. We will therefore linearize it, saying natural log of Q by natural log of C, and we can get 2 points and a line through them. This will essentially give us a way where we are saying the natural log of Q would be equal to the natural log of Kf times C to the n power, but if you recall, this will bring the n to the front. And we can also, instead of keep these both in one natural log system, we can rewrite this all as ln of Q equals the natural log of Kf plus n, because it comes out from the exponent, times natural log of C. So this then is our y equals mx plus b, or rather y equals b plus mx. So in this form, we have b plus mx, where x would be the natural log of C, m is our slope corresponding to n, and b would be our starting condition here. Okay. Does that part make sense? Okay. Then when we do that, we can find value for n equals 0.84 and a value for Kf equals 0.034. The units on this one should be micrograms per milligram per micrograms per liter, I think. Have something else written there, but I also have times 0.84 down here. I'm not sure what's up with that. Yeah. So yeah, if you use a log base to linearize, I think you probably ought to get the same answer. Same answer for n, or for which? Okay. It should come out to be the same, I think. I think this unit, by the way, is funny, and it does need to account for the 0.84. Different answer. Okay, so I'll take a look at that. Yeah. What do you guys get for n?
I got the same n, but I got a different.
Okay, what do you guys get for kf?
11.3 was what I got.
11.3.
Because I mean, when I plotted it, I got this like my y equals 0.84x plus 2.4, and then I did e to the 2.4 so I could get kf, and that's how I got all of it.
What was the 2.4 coming from?
The 2.4 is my b. Like whenever
Okay. When you took.
it, I got the equation.
Okay. Gotcha.
And so then, like, based on like what you were saying, like ln of q is y, ln of kf is b. So then when I did the e, so I could get rid of the natural log to
Yeah.
both sides, I got.
Yeah. And Lauren, what did you get for kf? Just something. Okay, so something completely different. Okay. Yeah, I'll take another look at this, and I'll send out an update if I find something. Like I said, I wish I was a little better prepared, And it's been a while since I solved that, so I may have done it wrong last time and therefore this time.
In my own case, I just like, since you have 2 points, you just set up 2 equations and then solve the chocolate and then get the end.
And what did you get?
I got the same answer you got.
Okay, this way? Okay. Yeah, I'll take a look at that because it sounds like we've got a graphical approach and perhaps the other way is a system of 2 equations kind of approach. Be strange for those to be different. Okay, so then that's all part A. Part B says, in fact, maybe I should just give myself the reminder here. Part B says, suppose that 30 micrograms of carbon tetrafluoride, were added to a third bottle, also containing 100 milliliters of water and 20 milligrams of GAC. And then the task is to estimate the expected final aqueous concentration. So just as a point of reference, we don't have a lot of time now. We'll probably just have to come back to the estimation part later, but I ended up estimating C at 67.1 micrograms per liter and a Q at 1.16 micrograms per milligram. Now, to do this, it's an estimation, and we do need to use kind of a guessing type of an approach. It's often hard in these systems to say where exactly is our value going to come out if we don't already know one of these parameters, right? If we knew Kf, that would be different. Perhaps we can get to it that way. Since these numbers are between, we can perhaps use our analysis here and make some estimation. But each time we put in a new value, perhaps we ought to estimate a new parameters. So I think the deal is reparameterization every time we add something in. So this problem, I'm going to just say, I'll try to come back and add some more clarity. If I can do that this week, I will, and at least give you some more, a deeper dive on the Excel side of things on another time. Yeah.
Sorry, how often can we do 4B? Because I estimated using a proportion from just one of the points that we had in part A, using a proportion with the 300 microliters to get like a C value, and it was 70.
For part B or for part A?
For part B.
Okay. Yeah, I mean, if you got 70 micrograms per liter, I think that's a pretty good estimate. Yeah. I'd be happy with that. All right. Any other questions? One thing you could potentially do is just taking a look at, kind of on general terms. In A, the final was 120 micrograms per liter, and in B, it was 19. It's going to be somewhere between those, for sure, right? Because those are kind of endpoint cases. Okay, I really don't have enough time to finish everything. I think I have a recording of the remainder of these problems. So I will post that for you in addition, but I will, for now, try to explain the process for each of these as best I can. So 7.3, we have activated carbon. Essentially, we're given a description of what's going on. We're treating batches of water to remove some organic. Each time we treat a batch, we let it settle, water is drained off, a new batch is mixed with the carbon. So we're reusing the carbon repeatedly. And the adsorption is known to follow a Langmuir isotherm after a number of batches of water. And doing this way, the adsorption density on the sample is given by Q equals Q max times K adsorbed times C in divided by 1 plus K adsorbed times C in, where Cn is the pesticide concentration of untreated influent water. So the value of Q under these circumstances is much less than Q max. So the Q max would be the maximum amount of adsorbent, of adsorbate that could be on the adsorbent. And then the question is, do you think that removal efficiency of pesticide in the next batch of water to be treated will be good or poor, and explain? So I think we need to take a look at our typical Langmuir isotherm. So we know that we're just given Q equals Q max just now times K adsorbed times C at equilibrium, or excuse me, at the input. Actually, you know what? I'll just write the typical. For typically, we write this as Q at equilibrium divided by 1 plus K adsorbed times C at equilibrium. And if we look at what we're provided, we see that they say it can be described as the influent, right there, with C as the untreated influent water in both cases. So if that's the case, then essentially what they're saying is C in is equal to C equilibrated. So that means we've filled up the carbon already, pretty much. So there's not really any sites left to adsorb because we've already reached equilibrium. If we had cleaner water, we'd have pesticides coming off to reach a new equilibrium. So essentially, we've done it enough times that there's not really any more space. Yeah. Okay.
Sorry, but it says that Q is a lot smaller than Q max.
Yeah.
And Q is how much pollutant is it on the carbon.
Yep.
So it's a lot less pollutant than the maximum pollutant.
Yeah.
So I think that it means that blue carbon was just a bad choice for, like, it's at equilibrium because it's not absorbing anything.
So I agree with what you're saying about Q is a lot smaller. That's important, but that's almost always the true for adsorption systems, because the Q max would be if we provided a solution that was pretty much pure, let's say benzene. If we're trying to absorb benzene, we filter pure benzene or put pure benzene in there. That's the way we'd find Q max or force it to Q max. But in this condition, we have a small amount of pesticide, so Q is typically less than Q max, but it is at equilibrium. So that's this problem's trying to throw you for a loop there, and it kind of got me at first as well. But that's actually expected and normal for operation. But what you were getting at there was it's a poor choice to reuse it because we've already reached the equilibrium. Your explanation was starting to get there too. So perhaps the reasoning there, just keep in mind, it's kind of like saying my water bottle is probably equilibrated with the atmospheric oxygen, but the maximum possible oxygen in here is nowhere near that because we could put 100% oxygen atmosphere in here, and then it would be more. So the Q max is a little strange that way. It's not specific to this circumstance. And the way I'm writing this here, no more space. It's not, we'll just say no extra space. If we forced it, if we jacked up the contaminant concentration, we probably would get more on there. So this would be poor performance accordingly. Okay, does that make sense? All right, so next up, we have 8.1. And we have data for the uptake of trichlorophenol on activated carbon. The initial TCP concentration was 100 micrograms per liter in all cases. So we go from 100 and then down to some final. So we can take a look as a function of carbon dose. We will have some final concentration with its small carbon dose. We remove just a little bit, going from 100 to 96. And if we have a big carbon dose, 8,000 milligrams per liter, we remove almost everything. So A, determine the best fit parameters for the fitting data for the Freundlich isotherm. B, I'll just go ahead and read these through and we will just get what we can. Essentially, A, we need to plot our log Q versus log C. B, an industrial plant must meet the effluent discharge limit of 1 gram TCP per day. How much carbon would be used per day in a CFSDR in which adsorptive equilibrium is reached quickly if the process flow was 600,000 liters per day of a waste containing 100 micrograms of this stuff. Okay, so that one's going to be a mass, kind of just a mass calculation, not even quite a mass balance fully. That ends up getting us, I'll provide solutions where it's written out for you, but that essentially gets us to 1,640 kilograms of activated carbon per day, which is quite a lot. Okay, then part C, how much carbon per day would be required if the stream was treated in 2 sequential batch reactors with half of the activated carbon in each. So doing it sequentially is going to change the amount that's coming in, could change things quite a bit. So for C, what we'd want to do is set up, whereas this case, we have that for B, and then C, we can look at it this way. And we will have a different Q in each compartment. And adsorption generally performs a lot better when we have a high amount of adsorbent compared to the adsorbate. So it does a very good job removing trace things, and not so good a job when it's a lot of something you have to remove. Okay, so that's really all I have time for, but I'm going to post a version of this where you can see all the solutions that I have for you. This one. So in order to plot this, the log Q versus log C, you just take this into Excel, take the log values, and do those calculations accordingly.
The first AC dose is at 2, it's 8.
You are correct.
Because, yeah, I don't have an outlier in my data. Like, in my graph.
That's why this looks so silly.
It's 8, and the final is 96.
I will correct that too. Thank you. All right. I'll email you No class on Thursday because you'll have the take-home exam. Question?